There is a particular kind of mind that cannot leave a problem alone once it has revealed a crack. Not because the mind is restless, but because the crack is an insult. It suggests that the world is not yet coherent. It suggests that the language we use is not yet worthy of the thing we are trying to describe. Erwin Schrödinger had that kind of mind. He wanted elegance, but not the shallow elegance of pretty symbols. He wanted the deep elegance that occurs when the form of an equation matches the shape of reality so well that the two feel like the same thing, seen from different sides. If you meet him first through the cat in a box, you might imagine Schrödinger as a prankster, a man who put absurd images into physics just to make a point. But that cat was not a joke. It was a warning sign. It was the sound of a brilliant mind refusing to let the new quantum theory harden into complacency before its meaning had been understood. Schrödinger was born in Vienna in 1887, in an empire already tense with complexity. Multiple languages, multiple identities, old aristocratic structures, and new scientific ambitions living side by side. He grew up in a home where education and culture were treated as normal and necessary. He learned early that the world could be described in more than one language, and that translation was not trivial. A concept in one tongue does not always land cleanly in another. That sensitivity, both to language and to the limits of language, would follow him into physics. He studied in Vienna and became steeped in classical physics, mechanics, electromagnetism, thermodynamics. He loved the old physics for its clarity. He loved the way a differential equation could take a system and make it intelligible. He was not born into the quantum revolution. He was pulled into it by the force of unresolved facts. By the early 1920s, quantum theory was in a feverish state. Planck had quantized energy to fix blackbody radiation. Einstein had treated light quanta seriously. Bohr had built a model of the atom with discrete orbits and quantum jumps. Yet all of it still felt like a patchwork. It worked, often astonishingly, but it did not feel like a unified mechanics. It did not have the inevitability that Newton and Maxwell had. Many physicists had begun to accept that the microscopic world behaves differently, but they had not yet agreed on the most honest way to speak about it. Then, in 1925, Heisenberg introduced matrix mechanics, a new and powerful formalism that built quantum theory out of observables and transition probabilities rather than orbits. It was correct, but it was strange. It replaced the familiar geometry of trajectories with an algebra of arrays whose multiplication did not commute. For some minds, that abstraction was exhilarating, not because it was wrong, but because it felt like a loss of contact with physical intuition. He wanted a picture. He wanted continuity. He wanted something that behaved in form like the field equations of classical physics. The spark came partly from Louis de Broglie, who proposed that particles like electrons have wave properties. De Broglie suggested that the electron's wave could form standing patterns around the nucleus, giving a natural reason for discrete energy levels. Only certain waves fit. This was a beautiful idea because it offered a bridge between quantization and continuity. Discreteness could emerge not from arbitrary rules, but from wave conditions. Schrödinger saw, in de Broglie's hypothesis, a way to rescue a kind of classical intelligibility without denying the quantum facts. In 1926, Schrödinger wrote down the equation that now bears his name. It is hard to overstate what that meant. The Schrödinger equation provided a dynamical law for the quantum state, a rule for how the wave function evolves in time. Instead of asking where is the electron on its orbit, Schrödinger asked for a wave function spread through space, whose shape encodes the probabilities of finding the particle in different places. The equation describes how that wave function changes. It is to quantum mechanics what Newton's laws are to classical mechanics, not merely a description of outcomes, but a generator of predictions. Schrödinger's wave mechanics did something else. It made the quantum world calculable in a way that felt familiar. Differential equations, boundary conditions, eigenvalues, these are the tools of classical physics, now repurposed. When Schrödinger applied his equation to the hydrogen atom, the energy levels emerged naturally, and they matched the known spectral lines. The old quantized orbits were not needed. The discrete spectrum was not imposed. It fell out of the mathematics like a truth that had been waiting for the right language. This is the moment where quantum theory stopped being a collection of rules and became a coherent mechanics. Even though matrix mechanics and wave mechanics were soon shown to be equivalent, Schrödinger's formulation gave physicists a new kind of intuition. It allowed them to picture atomic orbitals as wave patterns in space, shapes rather than paths. It gave chemistry a foundation. It gave condensed matter physics a tool. It gave the 20th century a method that would become routine, even as its meaning remained strange. But Schrödinger was not satisfied. The wave function seemed to describe something real, an amplitude spread through space. Yet experiments suggested that outcomes arrived as discrete events, a spot on a screen, a click in a detector. How could a smooth wave lead to a single localized result? Max Born proposed a probabilistic interpretation. The square of the wave function's magnitude gives a probability density. The wave function does not describe a smeared-out particle. It describes the distribution of possible outcomes. He wanted the wave to be a physical wave, not merely a tool for calculating probabilities. He felt that probability, if fundamental, was a confession of defeat. Here we meet the tension that shaped his later life. Schrödinger helped build the central formalism of quantum mechanics, but he did not accept the worldview many drew from it. He wanted a physics that described reality, not merely observations. He wanted continuity, not jumps. He wanted causality, not irreducible randomness. He was not alone in that discomfort, but he was unusually articulate about it. In 1935, Schrödinger proposed a thought experiment designed to expose what he considered the absurdity of taking the quantum formalism too literally at the macroscopic level. Imagine a cat sealed in a box with a mechanism triggered by a quantum event, say, the decay of a radioactive atom. If the atom decays, a poison is released and the cat dies. If it does not decay, the cat lives. Quantum mechanics, if applied without qualification, seems to suggest that before observation, the atom is in a superposition of decayed and not decayed, and the mechanism, and thus the cat, would be in a superposition of dead and alive. Schrödinger offered this not to celebrate weirdness, but to protest it. He was saying, if you tell me the wave function is a complete description of reality, then you must accept that the cat is both alive and dead until someone opens the box. That is not merely counterintuitive. It is a signal that something is wrong in the way we are translating the formalism into claims about the world. Schrödinger's cat has been misused ever since as a mascot for mystical interpretations, but its real purpose was to force clarity. It was a demand. Explain where the boundary lies between quantum superpositions and classical definiteness, or admit that the story is incomplete. The measurement problem, how a definite outcome arises from a superposed wave function, remains one of the deep, interpretive knots of quantum theory. Different interpretations answer it differently. Collapse postulates, many worlds, hidden variables, decoherence, and more. Schrödinger's cat is not a solution, it is a lantern shining on the knot. Schrödinger's own life was also marked by a refusal to fit neatly into the expected boxes. He was a man of strong desires, complicated relationships, and a temperament that did not blend easily with institutional conformity. He lived through the collapse of the Austro-Hungarian Empire, the rise of fascism, the upheavals of Europe. His academic career moved across cities, Zurich, Berlin, Oxford, Graz, and he often found himself at odds with political realities. When Nazi influence grew, he left. When Austria was annexed, he was in danger. He spent years moving, teaching, writing, trying to keep his intellectual life intact, while Europe tore itself apart. In 1940, he settled in Ireland at the invitation of Eamon de Valera, who founded the Dublin Institute for Advanced Studies. There, Schrödinger found a kind of refuge, a place where he could think and write without immediate political threat. It was in Ireland that he wrote one of his most influential books outside physics, What is Life?, published in 1944. That book is another clue to his mind. Schrödinger looked at living organisms and asked how they maintain order, how the stability of genetic information is possible in a world ruled by thermodynamic decay. He introduced ideas that would inspire pioneers of molecular biology. He suggested that hereditary information might be stored in an aperiodic crystal, a structure stable enough to carry complex information. Later, when DNA's structure was discovered, many saw Schrödinger's book as one of the sparks that helped make the question feel urgent and tractable. What matters here is not that Schrödinger predicted DNA in detail. He did not. but that he treated life as a problem physics could illuminate, without reducing it to triviality. He understood that life is an order-maintaining phenomenon that cannot be explained by hand-waving. It demands a physical account. His book helped legitimize the idea that the deepest biological questions are also physical questions. So Schrödinger's legacy spreads in two directions. On one side, he gave us the wave equation that made quantum mechanics calculable and powerful. On the other, he refused to let that power become a substitute for understanding. He insisted that physics should not be satisfied with a recipe. It should seek a coherent picture of reality, even if that picture requires new concepts. There is something almost tragic in his position. The Schrödinger equation became central, and the probabilistic interpretation became standard. The physics community, for good reasons, prioritized predictive success. Schrödinger's discomfort became, to some, an eccentric philosophical worry. But history has a way of returning to the worries that were set aside. The measurement problem never fully disappeared. It became part of the hidden foundation of quantum theory. Ignored when building devices, unavoidable when asking what the theory claims about the world. Schrödinger was awarded the Nobel Prize in Physics in 1933, shared with Paul Dirac, for contributions to atomic theory. The prize recognized the formal power of wave mechanics, but it did not resolve the interpretive struggle. Schrödinger continued thinking, writing, and arguing about the meaning of quantum theory for the rest of his life. He was not trying to destroy quantum mechanics. He was trying to keep it honest. If you want a scene that carries his temperament, picture him in the mid-1920s, refusing to accept that the world's deepest mechanics should be expressed only through an abstract algebra without a continuous picture. He goes searching for a wave equation, and when he finds it, the hydrogen atom yields its spectrum with a kind of inevitability. For a moment, the universe feels coherent again. Then, slowly, the realization returns. The wave function does not behave like a classical wave of water or sound. It behaves like a probability amplitude. The beautiful equation produces a reality that resists the old intuition. Schrödinger does not shrug. He pushes back. He builds a cat to make the problem visible. And in that pushback, he performs another service. He keeps the quantum revolution from becoming lazy. He reminds us that understanding is not the same as calculation, and that the most successful equation in physics can still leave us with an unfinished story about what the world is. You have been listening to Scientific Giants Who Changed Our Understanding of the World We Live In. Today, we followed Erwin Schrödinger from the invention of wave mechanics to the haunting clarity of a cat in a box, and then into the question of life itself, where he helped inspire a new way of thinking about heredity and order. In our next episode, we will meet Lise Meitner, a physicist forced into exile who explained nuclear fission while watching others take the credit, and who carried the burden of insight when that insight became a weapon. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear. If it moved you, bring a friend along next time. Until our next hour together, remember that an equation can be correct and still leave a moral and philosophical question behind. Because the world does not only demand prediction, it demands meaning.